What's going on, everyone? In today's lesson, we'll be going over the slope, also kind of called the gradient in some textbooks, of a line, and we're going to see how it can be applied to a couple of word problems in real-life scenarios. So let's get right into it. In a lot of textbooks, they'll call this the gradient. Perhaps if you're in the United States, this will be often called the slope. So we call it the slope or the gradient. It basically just means which are we changing in the vertical direction for every single change in the horizontal direction. Change in y over change in x is maybe how you heard of it, or delta y over delta x perhaps. But this basic graph right here is going to show us what this looks like. Here we have what's called a positive step, because as we are changing in the positive x direction, we're increasing in the x direction. We are also increasing in the y direction to keep this line. So it really is kind of a step by step by step. We're going over here, up here, over here, up here. And you can see that as I increase in the positive x direction, I'm going to go up in the y. So in that case, we'd have a positive slope. It's just change in y over change in the last part. So oftentimes we'll say that slope is equal to rise over run. And one way to think about that is that what you're really doing is you are subtracting the value of the y coordinates and you're dividing it by the value of the x coordinates. And that might be a sticking point for some of you, but honestly, it kind of makes sense, right? Because if you think about this as having a value, we'll go over here, of y2, and we go over here to have a value of y1. Well, then if you take from here, 0, all the way up to right here, and then you go from here, go all the way here. If you subtract those two, well, then you're just left with what's in the middle, which is how much this graph has increased by. So that's why we say it's y2 minus y1. And if we have x2 minus y1, well, right here would be our x2, because again, we are going from this point, going all the way down. Right there would be our x2. And then all the way over here, we would have our x1. And then if we just find the difference between those two, in this case, let's say we have 1, 2, 3, 4, 5, 6. Let's say that's 6. And let's say this is just 1. 6 minus 1 is 5. Then we'll find that this is 1, 2, 3, 4, and 5. Okay, so that's the reason why you see the subtraction problem often. And it's just called rise because the y is our vertical. It's how far we're rising or falling. And then run because horizontal. You run on flat ground, or maybe some of you people that are better shape than I am are running up a hill. But really, run is going left to right. Rise is going up and down. So if we take a look at example 1 here, very simple. We're going over 3. We have an increase of 3 in the x direction. Then we have an increase of 3 in the y direction. So my rise over run is going to be 3, that blue 3. And in fact, I can actually color coordinate these to be a little bit better. 3 all over 3. And 3 divided by 3 is just 1. So you always want to express slope or gradient in its simplest form. So it's a fraction, you simplify it down. If you can turn it into a whole number, great, do that. And now for example 2, again, I have rise over run. Rise is going to be my blue. So my rise is going to be what? I'm just going up 4. So I'm going up 1, 2, 3, 4. Perhaps it's easier for you to see on this side since we're starting here to go up 1, 2, 3, 4. Either way, you're going up 4. And then what am I running by? What am I going over? Well, I'm going over 1 and I'm going over 2. Going over 2. So it's going to give me 4 divided by 2. That's going to give me 2. Another way of thinking about this is that if you have 4 over 2, you're also going to be able to simplify as 2 over 1. And sometimes that might help with the whole rise over run image. Because if you think about it, it means I have to rise 2 and run 1 in order to get back to my line. So if you think about it, if I'm starting here, I'm going to rise 1, 2, and then I'm going to go over 1. 2 over 1. So that's why. And I could also go up 1, up 2, over 1. 2 over 1. So my slope is what we call 2. Just because 2 divided by 1 is 2. A little bit of a simpler way to do that. So now we look at something a little bit different. Again, I'm still going to have rise over run. So my rise is in this blue. And in this case, I'm actually decreasing down by 1, 2, 3, 4 units to get over here. So I'm going to have a rise of -4. Sorry, that's my laser pointer. A rise of -4. And my run is going to be 2. And that's going to give me a value of -2 over 1 or -2, depending on how you look at it. So again, what that also means is that I could be going down 1, 2 over 1, 1, 2 over 1. So I'm going -2 down, positive 1 to the right, and that is going to get me back to the line. So that's exactly what slope is telling us. It is this constant change that gives linear functions really their identity and their properties. That you're going to increase in y by a certain amount and then increase by x a certain amount for every single step of the way. Often represented as either a whole number or a simplified fraction. All right, so let's continue. All right, so let's determine the gradient or the slope, depending on which curriculum you're using, of the line joining these points 4, 1, which is A, and B, which is 8, 3. So I already told you a little bit about this, that if you take the differences in y's divided by the difference in x's, that's going to give you your change in y divided by your change in x, which will always give you your slope. Now, if I'm looking at this, I'm thinking, okay, I can actually go ahead and label this. A is going to be 4, 1, and B is going to be 8, 3. So it does not matter which one you call y2 or y1. What matters is that you are making sure that these two are paired up. That x2, y2, if you want to call that, are paired up, and that y1, x1, let's say down here, are paired up. And let me show you what I mean by how it doesn't actually matter. So let's say I'll call this one x2 and this one y2. All right, so let's say I have y2, that's going to be 3, which means that my other y would be 1, which would be right there, divided by x2, which would be 8, minus x2, which would be, minus x1, which would be 4. So if you notice, these are paired. 8, 3 is a coordinate pair right here, and then 4, 1 is a coordinate pair right there. So that's what I mean about matching those up. So I'm going to get a difference of 2, get a difference of 4, and get a difference of 1 over 2. And that should actually make sense because, again, this is rise over run. So I have rise over run. I'm going to rise 1 and then run 1, 2. I'm back on the graph. Going up 1, going over 1, 2, back on the graph. So this works. And so if I flipped it to where I actually wanted to consider this to be, where I considered this to be x2, y2, let's see how that would work out. So if my y2 was instead 1, I would subtract 3, because that would be my other y coordinate. Let's say x2 I considered to be 4, and then the other one to be 8. So again, these are still paired up. 4, 1, 4, 1, and then 8, 3, 8, 3. They're still paired up, but I'll show you why it doesn't make a difference because 1 minus 3 is negative 2, 4 minus 8 is negative 4. I'm going to get negative 1 over negative 2. That is going to give me a positive 1/2 because I'm divided by a negative number. So in each case, I would say that the slope, denoted by m, is going to be 1/2. And that will be my final answer for this specific question. Okay, so hopefully that sheds a little bit of light as to why the order doesn't necessarily matter, but what does matter is to make sure that your x2, y2, x1, y1 are paired up accordingly. Okay, you can always double check by doing that little test of just counting up and counting over every single thing. Which brings us to a kind of interesting question, which is what exactly is the slope or the gradient of horizontal and vertical lines? Because they're kind of weird, right? So here I'm looking at a line that's going over 1, 2, 3, 4, 5, but then it's not going up anywhere. So if you go back to thinking that slope is rise over run, in this case 0, because I'm not going up at all. And my run is going to be 5. And what is 0 divided by 5? It's just 0. So my slope here is just 0. But if I switched it to where I was like, oh, okay, well now I'm actually rising by 3, but I don't have any lateral movement. I don't have any horizontal movement. Well, so that means that again, if I'm doing rise over run, my rise in this case is 3, my run in this case is 0. And this might be a little confusing, but remember that if you're ever dividing by 0, that is an undefined function. So I would actually say that the slope here is undefined. So again, if you ever have 0 in the top, your answer is going to be 0. If your 0 is in the bottom, it's going to be undefined. And if you're confused on that, put it into a calculator. Put in 0 divided by 5, you'll get a 0. If you put in 3 divided by 0, you're going to get an error. Syntax error, undefined, something like that. Your calculator will spit out an error warning. Okay, it's that simple. Now, let's go ahead and take a look at a sample problem here and say, hey, what are the slopes or the gradients of these lines that I'm looking at here? Well, the easiest thing to do if you're ever given a graph and you're asked for the slope, you want the rise over run. So what you want to do is you want to focus on easy points. This isn't exactly an easy point because while it clearly crosses x equals 1, it's not exactly certain what this value might be over there. So what you want to do is find out where it crosses both of those kind of miniature lines, so to speak. Okay, kind of the minis axes or something. So right here, I have a definite point. I have a point of 2, 5. And then let me look for another one along here. Oh, there's one right here, which is going to be 4, 4. So I'll write right here. I'll write 4, 4. And you only need 2 points. That's all you need. So again, if I know that my formula for slope is going to be the difference in y's, as long as I have the correct order of these, I'll get the right answer. So let's go ahead. I'll say y2 is 4, and I'll say y1 is 5. So I had the 4 here and the 5 there. Let me go ahead and divide it by, let's see here, 4 minus 2. I'm going to get negative 1 all over 2. I'm going to get negative 1/2. So is my slope indeed negative 1/2? Let's see. That means the implication is that I'm going to go down 1 and over 2. So negative 1, positive 1, 2. Negative 1, positive 1, 2. Perfect. Lines up, so everything's fine. So in this case, that is the answer. The slope here is just 1/2. Okay, so let's take a look at a different problem. Let's say, okay, I want to know the slope. I'm looking. There's a really good point, which is going to be 0, negative 1. Let's find another good point right there. That is going to be 5, 1. So again, my slope is just the difference between my y's to find the height and the difference in my x's to find the run. So let's say that y2 is just 1. Let's say y1 is negative 1. Remember those parentheses, very important. And we're going to divide by x2, which is 5, and x1 is 0. That's going to give me 1 plus 1, because again, minus a negative, plus all over 5. And that's going to give me a slope of 2/5. So is this actually true? Let's find out. If I'm starting here at the point that I know, and I'm going to go rise 2 and run 5, all in the positive direction. I'm going to rise 1, 2, and I'm going to go over 1, 2, 3, 4, 5. Boom, I'm right there. That's the correct answer. All right, so from a graph, it's just that easy. Just find 2 points, follow the simple formula, and you'll get it. Look at an example which might model more of a real life situation. Okay, so let's say that a funicular tunnel, kind of an interesting, interesting word there. What does funicular mean? Train on a steep slope. Fun fact about funicular: it's just a steep railway, pretty much. I just had to Google it myself. All right, but basically, imagine that there's several different stations. Okay, and let's say that one of those stations, A, if you just lay it on a nice coordinate Cartesian plane, is going to have a coordinate of 30, 60. And let's say that it's going to be about 60 meters above station 0 at about ground level. Now, station B, on the other hand, is going to have coordinates of 230, and then we're going to have this missing value h. So all coordinates are going to be given in meters, and we know that the slope or the gradient of this railway segment is 0.6. We're given a decimal, not necessarily a fraction this time. Find the height of station B above the ground. Okay, so let's think about this. Station A has coordinates 30, 60. So you can draw a coordinate pair if you want. I'm personally not going to. I'm just going to mark a circle here, and I'm going to mark it as A, and I'm going to say it has 30, 60. Okay, station B is going to have 230 H. So I know that I'm going to have some kind of station over here, B, and it's going to be 230 with some mystery height H. Okay, and there's going to be some kind of choo-choo train track connecting these two. Okay, and I know that the slope here is going to be 0.6 or 6 over 10, which is also going to be 3 over 5. Again, different ways of representing the same thing. And now I want to know what the heck is the H value of this? How high is this thing? So let's figure that out. Now, if I'm looking at this, I know that my slope form is equal to y2 minus y1 all over x2 minus x1. So let's go ahead and plug in all these values. I have m right here. That can go here. I have a y2, I have a y1, I have an x2, and I have an x1. Okay, so let's actually just write that out. 0.6 is going to be equal to h minus 60 divided by 230 minus 30. So now all we have to do is a little bit of algebra and we'll get the right answer. So now this is representing more algebra and kind of like 2-3-step equations. But let me go ahead and simplify this down, h minus 60 to b over 200. And again, my variable that I'm looking for is this h, this height. So I want to get it all by itself. So what I'm going to do now is just move the 200 over. So I would multiply each side by 2. All right, so this will cancel out, cross cancel. So in this case, I'll have 120 is equal to h minus 60. And what I'm going to do now is add 60 to each side because I have this negative 60 lingering over here, which is what's stopping me from keeping h all by itself. So I'm going to add 60 to both sides. This, of course, would cancel out over here. I'd have 120 plus 60, giving me 180. That is going to be my final height. So what that means is that at a height of 60, this is going to be at 30 on whatever kind of coordinate system they laid it on. And then whenever I bring this value up to 180, I'm going to have 230. So that's how you can use the slope formula and missing one of those coordinates along with the slope and kind of move these things around so that way you can figure out what the missing value is. Okay, so it's really just kind of some things that you might have learned in Algebra 1 or Algebra 2 with 2- and 3-step equations, now just overlaid with the slope formula and a little bit of context. That's the only difference. So I hope that sheds a little bit more light into what slope is, the formula, what it looks like on a graph, and how to manipulate that formula to solve for a variable that you need to find out the value for. Okay, and in our next lesson, we'll be going a little bit deeper into slope and how it can be used in mathematics. All right, take care and have a good one.